Okay, so I don't see the recording. I see it started now. Okay, perfect. So, welcome everyone. I see some people are still coming in, but since we are recording, we can just get started. And the first few minutes will be right interesting from the start, of course. But then it's just too bummer that you're a little bit late. Right. So, thanks everyone for being here. We're going to talk about quantum technologies today, and specifically quantum computing. I'm very excited to share to host this tech talk here today. My name is Julia van Velzen. I work for TIV, so Group Technology, and I have the pleasure to lead the Capgemini Quantum Lab. And I have with me here today Sam Gamway. He is also part of the Quantum Lab and also from Hybrid Intelligence. Sam is my friend and colleague who is really expert on quantum technology. He has a PhD in the field, but really also understands how this works in the market. Specifically in the case, I think this is one of your industries that you're very focused on, but specifically also in the case of life sciences. So we're going to a little bit take it as a example of how quantum technology and how quantum computing works. So let's get started. So maybe. So Sam, you've been working on this for quite a while. Is there something particularly that you are, why are you in this field? Is there something that really excites you?
Well, I think the possibility of I think the possibility of quantum technologies in a commercial setting is really incredibly exciting in general, because what we're really talking about here is a new paradigm of compute. We're talking about, in some cases, things that not only are not going to be possible, not are possible today on conventional computational hardware, but in some cases we're talking about things where we actually know that they will never be possible, right? We know that there are some examples, and we'll talk about maybe some of these later in our session, where, if you like, the number of numbers involved is more than the number of particles in the universe. So however big your HPC is, you simply won't be able to do that. And some of the examples, for example, in the life sciences, where we're talking about molecules and their interactions, really neatly fall into this space. So from that point of view, I think it's just truly exciting because it's something completely different, and it's reaching maturity.
Absolutely. So I completely agree. Like, it's this mind-boggling, weird concepts from how particles interact on the quantum scale, the nanoscale, and the even crazier things, you can actually do something practical with it, right? Things that have never been before, that would never be possible otherwise. So
Absolutely.
if we go to the first slide, I think that we can dive right into it, because I think there's loads of content to cover anyway. So let's get into it. What do we see here?
So good question. Right? We thought at the beginning we should show a picture of a quantum chip, and partly to highlight that actually, if you just take a step back, quantum just could look like, well, it's another way to do computation. This here, it looks like something that might be in your laptop, right? If you were to take the back off it. But of course, this is something very, very different. This is one of IBM's most recent quantum computer chips based on superconducting circuits. In reality, as some of you may know, there's a lot of equipment around this, so it doesn't just look like this. But the crucial thing is this does a completely different set of operations, and the scale today is such that, sure, this chip is probably not going to do things which are going to be completely transformative in a commercial setting, but the children of this chip, in a technological sense, maybe the sort of grandchildren, the great grandchildren, this is where over the few years ahead we're going to see sort of real transformation, I think.
Yeah. So there is also the other pictures that maybe some of you guys have seen, where you see these big chandeliers with all the golden things, and basically I use that picture quite often because it shows a different image where it's completely radically different, and where if you zoom in, then basically only the very tip of the whole thing is actually the quantum computer, and everything else, the refrigeration systems, and and I think there's two important messages here. One is, it's another computer, the fundamentally different computer, but it's extremely good in some things. And second, it's very different, but it's good at certain type of things. And I think it's also interesting to see like how that's developing, right? Because if you look at the first computers 60 years ago, the huge system like vacuum tubes and everything, they were also incredibly I mean, they probably looked more complicated than the computers today.
Yeah. Yeah, and I think we're in a similar phase, right? So this picture here, yeah, is deliberately chosen to sort of emphasize the similarity, but we're probably in that sort of equivalent stage where this technology will progress and quickly, and it's really exciting. But we're probably in a sort of similar state to those those people who were working on these, enormously large computers back in the early days of classical computing, where today we think, whoa, there's a lot going on there. And in a sense, history tells a story, right? We saw over the years from that point onwards how just progressively the impact of compute on functions all around the globe had a colossal impact.
Yeah. So can you say a bit more about the progression? So I know we have a slide about it as well. So where are we now?
Yeah, so maybe let's actually just put the items on this. I mean, it's a good one for people to guess what these points might be, but there are so many things you could select here. But you're looking at just the sort of last few decades and a measure of compute. So I mean, this is floating point operations. It's not speed, it's an absolute. There are many ways to plot this, but I guess the interesting things are, if we look to some of these points mentioned here, we start with the moon landings, where sort of some several billions of operations over a few hours were needed to guide the spacecraft down to the surface of the moon. And this is an example of compute really being an enabling technology for things which had just simply never been done before. Right through to the modern era, where we see, I think, from the late 90s, orders of magnitude more compute operations in a smaller time as well, because this is a game of chess where you only have, I think, 3 minutes to make that decision about what to move next. But this is an example of a computer beating humans at something which humans are really, really good at, right to the era of AI. And I think we probably can't avoid the topic of AI because it's just such a compute intensive industry. It's amazing. We look just over the last decade from AlexNet in 2012, the first time computer vision was really sort of transformative. You can do that on your laptop, right? This stuff, that's where this is, to GPT-3. And I think everybody's heard of the examples of the model which can generate text, which is so convincing that a human a human can be convinced that it's actually written by a person. I mean, this is so many orders of magnitude more. I think the figures are that it's something like I think the figures are that it costs somewhere between $5 and $10 million to train this machine learning model, and the environmental cost is like driving your car for nearly a million kilometers. This is the sort of scale of compute we're talking about. And quantum will be, well, I suppose the question is, where's quantum?
Oh, I guess that's a little bit tricky question, right? Because we are measuring here floating point operations, and quantum computers are fundamentally different.
Exactly.
So it won't be possible just to directly, point in the same scale. But I think what it does show is that this is increasing such a rapid pace, and there's such amount of compute power necessary for GPT-3, and of course there's already newer versions that require 10 or 100 or 1,000 times more already. It's completely unsustainable. There's no way in which we can increase this current pace. We just don't have enough space on Earth to have all the computers. Even if we have every space occupied with a supercomputer, it won't be enough to fulfill our needs.
I
we have
agree
to come up
completely.
with something new.
I agree completely. And I guess the natural question is, well, have we reached the pinnacle of everything we want to do with compute? And I think the answer is no. We're just barely getting started, right? I mean, great though this is as a model algorithm. It's it's unable. If we just focus on AI, it's completely it has many challenges in being able to reason. Examples like you feed it your life story and ask some sensible questions like, how many uncles and aunts do you have? It will probably give you a number, but not the right answer. So it's not able to tackle all of the cognitive challenges that we face. But if we look to other areas of compute, and I'm sure we'll come on to some of those, these are also just off the scale in terms of.
So let's dive right into that. So I think we have a couple of use cases first to explore. And the first one is really something that you have been working on a lot, something that I think is extremely promising. What do we see here? Why do you think this is an exciting use case?
Yeah, it's a good place to start for me, because, as you say, I'm really interested in this. So hopefully from the picture it's clear we're talking about the life sciences industry, we're talking about healthcare. And we'll probably maybe later come back into some specific cases of things we've been working on. But I guess why is this sort of such an important area? Why is it so exciting? Well, I think it's all come to the sort of top of people's awareness over the last couple of years is the first thing to say. I think we've all recognized that the life sciences industry plays a crucial role, especially when we're faced with a global pandemic, and the solutions to that, to enable society to reopen and for enable us to sort of get back towards normality, are therapeutics. They are vaccines. This is an incredibly important industry. But I think, sort of looking beyond that, there are still many problems which are unsolved in this space. So not all diseases are curable. Many diseases have very little treatment in the way of treatments at all. Discovering drugs is really, really, really difficult. It involves huge numbers of experiments, often with huge amounts of laboratory parallelization. But everything that you can do in a real physical experiment is kind of a drop in the ocean compared with the entire design space for a new drug. And this is where simulation comes in, right? This is where the idea of going in silico comes in. And I think we hinted at this at the beginning, or I did when I gave my sort of first answer about what is exciting me. Drug molecules interacting with entities in our body, with proteins, with things that are involved in disease. These interactions are all quantum mechanical in nature. So while today we can come up with effective models and we can use bits of AI, but use machine learning techniques to make predictions about what's going to happen, and these are helpful, we're actually quite a long way off from actually being able to simulate the real world. And I think this is just one of the areas where quantum computing is going to have an absolutely disruptive role over the years ahead as we look forward.
Perfect. So we're going to come back to that one a bit more later. Maybe if you can move 2 slides ahead, there is a question also about the encryption. So this is one of the things that quantum computers are good at, is to find patterns in large sequences of numbers, and that will also break cryptography. So there's one famous algorithm called Shor's algorithm, that will have an exponential speed up. And so it will break things like RSA. So the question was, when will today's encryption be rendered useless? So first of all, there's 2 algorithms. First, there's the Shor's algorithm that's an exponential speed up for RSA. So that will really be completely broken whenever the computers are ready. So when would that be ready? Well, that's really hard to say. No one really knows. But I mean, you could say that these type of quantum algorithms, they need a very deep circuit depth. So they need at least a couple billions operations before they come to their answer. And the problem with current days computers is that they are so noisy that you can't, every time you do an operation, there's like 1 in 100 chance or so that they will break down. So you can't really go more than 100 steps, because then the error will be so big that the result is unreliable. So in order to get to those, millions or billion steps in computations, you need to have error correction, and that it quickly adds up that you have like thousands of qubits for every logical qubit to do the error correction. So it quickly adds up that you need a couple of million qubits for that. So it's not there yet. Experts varying in opinion. Some say it could be 5 years, 10 years, 20 years. I think one important part here is that it's not about the realistic dates when this is going to happen. It could be realistically maybe 10 years, but I think because the impact is that big, it's much more advisable to look at the worst case scenario.
Absolutely. So a quick question for you, I suppose. What do you think people should be doing today about this problem, given that there are unknowns about when, but it's a absolutely sort of genuine and proven risk? What should we be doing?
Absolutely. So there are other types of cryptography that are being developed, and there was something someone had mentioned in the chat as well. There's the NIST, the National Institute for Standardization Techniques, that are building new classically algorithms that are capable of withstanding this threat. They are still in development, but actually yesterday or this week somewhere, they made a final announcement that they have a couple of algorithms that they are going to finalize, to standardize. But besides that, there is so much work that you can do today. You can start building crypto agility systems. You can build an inventory of what's vulnerable. If you look at signatures, for example, see how long they are valid, try to map them, how sensitive they are. Things like things like digital health records, they have to be sensitive for a long time. Think about your hardware constrained systems, for example, your embedded systems. They also take they might have more difficulty to update to newer encryption. So there's all kinds of things to start working on making your systems ready to be able to have the newer type of encryption.
Mm-hmm. Mm-hmm.
It's a whole topic by itself, so I don't want to dive too deep.
Of course.
Into that.
But an important and fascinating one. So, shall we move on to talk a little bit about, at least give a bit of a high-level discussion of how quantum computers work? I mean, as you mentioned at the beginning, I think this is, you could spend decades on this topic and get sort of different levels of very deep and profound understanding. But perhaps we can give a little sketch of how these pieces fit together and why. So I was going to sort of start by talking about ones and zeros, because I think we all know that classical computers, even if we are programming them in a much higher level abstraction, whether we're writing Python code or even formulae in Excel, under the hood we're dealing with zeros, we're dealing with ones. Manipulations are being done to these operations, and this allows us to perform all the calculations from I don't know, simulating the next mega factory, right, to doing our tax returns. This is the sort of stuff which is going all of the time. And I guess the sort of ingredient, or one of the ingredients in quantum, is that we don't just have zeros and ones, right? We have quantum states, which can look like a 0 or 1. We put the funny brackets around to denote this, but they can look like this, right? We can be in states which are a superposition, the sort of 0 and the 1. And people often talk about Schrodinger's cat as the sort of the quintessential thing about quantum physics, right? But this is really what's going on. This is the bit of physics that we're using in these things. So I think that's a nice thing to draw on. And of course, it's not just 0 plus 1, 0 minus 1, any kind of combinations of these sorts of these what are known as quantum bits, qubits. But the magic doesn't really happen with just one. It's a kind of nice party trick, this idea that we can be in a 1 or a 0 or both in any different kind of way. I guess the magic comes from sticking lots of them together, and how can we create algorithms on that space? So I've put 20 ones and zeros here. This is 20 bits. This is a pretty small small amount of information on a classical computer. But if we look at the quantum equivalent, actually 20 qubits in general can be in a state which is any combination, a superposition of all of the different combinations of ones and zeros. And so we can have all of these different amplitudes, A1, A2, all the way up, and actually there are about 1 million of these, right? So with 20 qubits, we are encoding something which has 1 million amplitudes involved in it, and you can see that therefore to represent that on a conventional computer requires a lot more resource. Now, it doesn't stop at 20, 40. Just because of exponential growth, we go to 1 trillion. And by the time we're at, say, 200-300 qubits, that number of amplitudes is more than there are particles in the visible universe. So that sort of gives some indication as to why quantum. And I guess what we haven't shown here, and I think we won't sort of prove to people today, is that there are algorithms on top of these qubits that can leverage these properties in order to do things which are truly different. So the fact that there's this sort of strange equivalence here is powerful. The real sort of art is actually in using this to do useful tasks.
And maybe to add to that as well is that the current systems that we had that are on the market today are around 100 qubits or so, depending on the vendor and the type. And so that you see that 100 qubits, that's already way past 1 trillion amplitudes. So that's already so big that it doesn't fit into normal computers anymore. And that means that you can't simulate your work directly. And that you also get all these interesting things that that you can do experiments that are not possible on classical computers, but you can do on the quantum computers.
Yeah, absolutely. I guess sort of 50 qubits is about the point where you can perhaps, if you really were to get access to some of the world's biggest supercomputers, you can probably just about, but I mean, it's a colossal effort to be able to do that. But just a doubling because of the exponential growth here means that, it's just completely blown out the water in terms of being possible, right? You cannot hope to simulate it.
So that was what these supremacy experiments were about, to really do something that classical computers could not do, regardless of how useful it is. And so we're really at that point where we are at the tipping point where we start to maybe do something useful. So can you explore a bit deeper, Sam, what the kind of things that could be useful?
Yeah, very, very good question. So let's come back up to the high level a little bit and stop talking about the details of qubits and just focus on the sort of broad areas. And I think there are three. We've already touched on simulation in a little bit of detail because this is one of the things that excites me in the life sciences area. So clearly relevant, and in particular simulation of quantum systems. If you really need to be able to do this at any modest scale at all, and do it in an exact way, then you're going to need a quantum computer. But it's not the only area. So we're seeing optimization problems, very very complex, high-dimensional combinatorial optimization problems are thought to lend themselves very well to quantum computing challenges. And the whole area of machine learning is a particularly interesting one, because there are many ways in which quantum computing might have an impact on this field, which is already so dominant around the world across applications today.
So for me, a bit of intuition why machine learning could be well fit for quantum computers is because the quantum computer has a huge space, like all these amplitudes where you can encode your information in, and that somehow your data is better represented in this large space because you can map your data much more efficiently. It's sort of like a kernel method to put something in the higher dimension of the quantum space.
Absolutely. I think that's one of the sort of areas that, well, we've been exploring, as you know, and other people have been looking at. The fact that you've got this exponentially growing space with number of qubits means that actually with a modest number of qubits, you have access to a huge amount of complexity. And that's certainly one of the routes where machine learning, where quantum computing could have a big impact on machine learning. I would throw into that, actually, if the data going into your machine learning algorithm looks like some of these objects on the left-hand side, where it already lives in that very high dimensional space, there's a natural link here. So machine learning in domains, it's not the only, by far from the only space, but I could pose it the other way around and say, if you want to do machine learning on this really sort of high dimensional data here, you're probably going to have to use a quantum computer, because it's the only way to push it into a computer. But I guess it's not the only route. I mean, do you want to make comments about or any thoughts about the potential future speed-ups that might come, and where you think we are as this, because it's obviously very much a sort of a research area still today, but there's excitement about the future of machine learning on quantum computers from that perspective too.
So I guess for many of these algorithms, there are two approaches, right? There's either you have this more or less heuristic approach where you be able to map something better in your quantum domain, and you scale something up because you use this sort of extra dimension of your quantum systems to represent your data and then do efficiently. But another way is to do the linear algebra faster on the quantum computer. So there are all these algorithms that, well, for example, the Shor's algorithm to do breaking cryptography very fast, but there's also algorithms to do linear algebra very fast. And of course, that's one of the building blocks of basically everything in our lives, including machine learning, backpropagation, or principal component analysis, or many of those things rely on linear algebra. So if we can speed that up in a more exponential way, then of course we can do loads of things better. So there is a question from two questions actually about the audience from about digital twins, and maybe in particular interesting in the case of healthcare. I think digital twins, I mean, for me it's a little bit broad topic, right? That could involve a bunch of things. What is your perspective? Where do you see digital twins overlap between those three areas, and how do you see that quantum could benefit?
It's a really good question. So I think it's fair to say that things always get interesting when you bring two, either emerging or growing technologies and think about how they interact and how they might interact down the line. And digital twins is a great example for that. For me, the first place to look is the simulation, right? So with a digital twin, that ability to get that sort of real-time insight from whatever system you're looking at is obviously incredibly powerful. And I think if we look to examples like, for example, the life sciences space, but also other areas where we maybe involve materials or other problems which are sort of quantum mechanical in nature, to get that sort of equivalent picture of what is going on here, what is my digital twin of this that gives me the insight of what's going on. If it's quantum in nature, then it will have to involve quantum computation. So if we wanted to have a digital twin, for example, of what is actually going on when we create a treatment and we bring that to a patient with a particular genetic makeup. Now, this is a way in the future sort of topic, but you can imagine the only way to really sort of faithfully simulate some of these things eventually will be with a quantum mechanical description, and therefore I think, yeah, the simulation space is particularly powerful.
Great. So let's move on. I think we have a question prepared on Mentimeter. I think Ishmeet, if you can share that one, because we'd be very interested to get your perspective as well. So if you guys can go to this website, menti.com, and enter the code. So that's 9757583, and log in there. Let me do that as well. And then we'd be very curious to hear from you guys what you think, what industry would benefit most. Maybe from your own experience, maybe something you read, maybe from what we've heard today. So, what are your perspectives? Let me also enter some. Okay, so we have services, life sciences. So I personally, I did some work also in financial services, and I think it's a very interesting area. There a little bit of caution, like sometimes life science or financial services is one of those industries that invests in every new technology just because they want to be on top of everything. And it might not always be the best fit, but there is some very interesting things, I think. And I think some of those things actually are not too different from what we see in life sciences. For example, Monte Carlo type of simulations. Yeah.
So what would be a sort of it's a tricky question to answer, right? But what would be a top couple of applications in financial services that, if you had to sort of give us a bit of an idea about where quantum computing could have that impact?
So there's a bunch of things. So the thing is with where people are exploring, it's I think it kind of converges to a few use cases actually. So the thing is that financial services is really built on these stochastic models, right? So you have variables of the market and of macroeconomic variables and all kinds of things that are very stochastically by nature. And to build the models on top of them, you get all these different scenarios that you want to explore. And then you want to explore different parts of the scenario, maybe explore some tail risks. And all those things are extremely difficult because you have to take billions of samples and it gets out of hand very quickly. So there's a couple of things that are related to this. For example, pricing of some financial products like options and other stuff, derivative pricing. Massive market. I think yearly there's like 10 times the world GDP is traded, right? Mm-hmm. So you can improve that a little bit, then you already have a very good business case. But also very other things like risk management, trying to reduce the total amount of reserves that you have to or no total number of capital that you have to reserve in order to meet regulations, fraud detection and management. All kinds of things, actually.
So do you think it will actually change some of the products that are offered in financial services eventually, or do you think it will just kind of speed up and enable more efficiency in the industry as it stands today?
So I think for financial services, but for most of these things, it's probably more in the background, right? So you don't like AI is quite in close to the customer, and you see all the things it does. I think for most of the quantum computing, it will be more in the background, and there might be some quantum part of it, but you might not actually know. Yeah. But for example, in derivative pricing, right, to have to buy an option that is better priced or that is more frequently priced, like for example, some exotic options are priced only once a week or something, and if there will be banks that price them every day, there is some benefit to hedge risks or for clients. So that will be definitely new products, but also things around know your customer kind of things, to have more specialized like fraud detection. Maybe there will be a fraud detection as a service or something. That can be real time, much more elaborate, much more dimensions. So definitely new products. So what about you, Sam? Any of those? So one of your areas is life sciences, but something else you want to highlight?
So I was looking here, and one of the things I thought was quite interesting is to compare the word cloud we're seeing with actually some of the areas we've been engaged in the quantum lab, right? And I think one of the things which is nice to see is that we are seeing some agreement in this audience between some of the areas that we're focusing, right? So I see life sciences, financial services appearing quite a dominant way there. Bits of organic chemistry and pharmaceuticals around, all sort of fitting into that space. And of course, there are other applications there. But I also see that we're seeing automotive pop up, and we're very much aware that the automotive industry is engaging with quantum technologies today and understanding where it will have an impact, everything from the optimization of routes to sensor placement to image detection algorithms and so on. So I think this is another nice one to draw on there. Do you see any that that surprise you, actually? I suppose that's the question.
What I was thinking was that one of the things that's not here, what we are increasingly seeing, is energy.
Yeah.
So you also have some background in the energy sector, right? Can you tell some of the why should it be in here and why isn't it?
Well, why it isn't is a good question, and I think it's maybe because it's not necessarily reached a wider audience so much in terms of the potential impact. But I think it's an interesting area because it's itself undergoing a transition, right? We are seeing the impact of energy transition, so the use of renewables, the fact that generation is no longer localized, but also on the demand side, the rise of electric vehicles is going to is having and will continue to have a huge impact on energy grids around the world. And this means that in that space alone, there are absolutely colossal optimization challenges to make sure that everything runs smoothly and as effectively as possible. Even things like how you plan maintenance, let alone how you balance the grid, as it's changing, will become different and exciting new challenges. But then there's everything that goes right back to the sort of material space. So when we see sort of organic chemistry in there, and if I can extend that to sort of material science more generally, there are areas like battery technology where of course the ability to simulate is going to have a huge role there. So I think across the board, energy, a very important sector to mention as well.
So let's move on. So one of the things we want to cover is to dive a bit deeper into one of the sectors, particularly life sciences, not only to explain how quantum and life sciences works, but also just as an example to see the journey that some of our clients are taking and some of our experiences there. And Sam is I would say definitely the expert within Capgemini on quantum and life sciences, but also one of the few experts I would say in the world that really knows this. So maybe to start, why quantum and life science? Why drug discovery particularly?
It's a good question. So I guess the start point, and I'm just trying to bring the deck back up here and bring a slide up, which sort of illustrates a big challenge in the life sciences and puts it all in one place. So hopefully this is coming through. You see a graph showing the investment in R&D over the decades, and this is just to highlight that a big challenge is actually bringing new products to the market, getting them to patients. So this exists outside of quantum. Let's just focus on why sort of a revolution in compute is really necessary in this industry. You see that the number of drugs brought to market which actually reach patients and have some benefit has been falling actually exponentially, decade on decade. Okay, this data that I got here only goes to 2010, but actually the evidence is that this carries on, and it actually takes a while to see the data come through from the R&D investment. So our window is always a little bit behind. So the question is, how can quantum impact that? Well, I suppose one of the first things to look at is sort of what are the reasons for this? Well, we have very high failure rates during drug development. So even when we've discovered a new drug, when we start to push it through clinical trials, most of the time these compounds fail, often just because they're simply not sufficiently efficacious to have the impact that they need to have on treating disease. It's incredibly expensive. You could have got that from the previous picture, but along with the great cost is the timescales. So you're investing a huge amount, and it takes a very long time to realize the benefits from that investment. Actually, when you do reach that, I mean, it's a good thing that that patent law is designed the way that it is. It brings many benefits to healthcare, but it means when you're at the R&D stages, you will have real time pressures to bring new products to the market, because actually you only have a finite number of years before other companies can start making generic drugs. They can bring the price point down, and you actually, at that point struggle to reclaim that investment that you've already put in. So it's a very expensive. It's why we see most drug companies are very, very big, because you have to be of a certain scale to be able to take on these risks. And I thought I'd just flag up an example actually from the recent Capgemini Research Institute report. I mean, to be clear, I would have said exactly the same things as this, but the exciting thing about quantum computing is that potential to cut the timescales down by being able to take more in silico, so do more on a computer and explore more on a computer, and get a better understanding of the potential candidates that are being taken through the R&D pipeline to reduce that. Reduce that chance of failure later in the process. So that's the high level on the industry side. Perhaps should we talk a little bit about the kind of where quantum comes in, and maybe I can share a couple of examples of things we're looking at, if that would be
yeah, perfect. And I will
relevant.
share the link to the research institute in the chat here, so that everyone can have a deeper dive into it. And I think it's quite interesting because it goes, well, one part explains what quantum is and everything, but most of it really has a long part of what our clients are doing and why and how we can support them in their journey, right? So I think it's a really like a handbook that we can use to speak to clients almost.
Absolutely. Sorry.
So, but then I'll put it in the chat and then invite you to read it. But let's indeed move to how then will quantum help with drug discovery?
Okay, fantastic. So the first point is that I've already spoken about simulation, and I'm now going to say a few words which actually maybe don't give a negative impression, but I want to highlight that this is an ultimate goal in this space. It's we can simulate at very small scales today. As we move into future generations of quantum computers, and we move into the regime where we can really begin to adopt error correction at scale, we move to a fault tolerant regime, we will reach a point where we can actually do simulation at interesting scales. But we're not there yet, and probably the scales which are relevant for the sorts of molecules that we have in drugs are probably going to be quite a few years away to actually really be able to do that on a quantum computer, especially when we consider that we're not just interested in this guy here, which is a molecule. In fact, this is a paracetamol molecule for anybody interested, so a pretty well-known drug. But we're interested in also being able to understand its interactions with other things, and that makes our problem space quite a bit bigger. So a couple of areas that we've been looking at, and one of them is to come back to the question of quantum machine learning. So one of the things we've been looking at is predicting the properties of molecules. Drug molecules have to have many good properties for them to progress through R&D and ultimately become a new product on the market. They have to be safe, and that's the most crucial thing. The fact that they must not be toxic, so that people can take them safely and they won't have a negative impact. So this is what we're predicting here. But there are any number of other properties concerning how they're absorbed, metabolized, whether they're soluble, whether they're easy to synthesize in an industrial setting, all of which have to come together, along with, of course, the drugs performing their desired function in an effective way. So many challenges. We've actually focused on tox as an example because it's a very, very important one. And we've asked the question, can we use quantum machine learning techniques? In particular, we were looking at some of the kernel methods we hinted on earlier to predict. So you got this idea here, this super high level cartoon of all of these molecules and their data entering. And I'm just going to show a picture here, which is a really high level picture of some idealized sort of two-dimensional data. Now, molecules are high-dimensional objects, but this is looking at some of those classifiers of tox. So if you like, the orange regions are toxic and the blue regions are non-toxic. And we're actually looking at a classical kernel with an equivalent quantum kernel. And the one thing I just want to say here is, in 2D, you will struggle to really sort of see what can be done with a quantum algorithm, because it's a very simplified example. But there are 2 points to take away. We've shown that these methods do work, the first thing, and that the models look different. Their expressivity is different, and that gives us a lot of a lot of interest in pursuing these further in the space of making predictions around drug molecules. Now, we haven't just looked in 2D, we've actually looked at data sets in higher dimension which take features from the molecules. But what we're moving on to do now is actually really use the quantum description of molecules. So molecules in these pictures look like balls and sticks. You can see little lines joined, sort of representing bonds between atoms. But what really determines the properties of molecules are their electrons and the states that they're in. And this is all quantum mechanics. So what we're looking at, and what we have an active research program around, is taking that data, which is quantum in nature, and coupling it with data-driven approaches, i.e. machine learning, in order to actually be able to provide better predictions into the drug discovery process. So that's one thing we're doing, which is particularly exciting.
So indeed, so this, what we see here, and if you go to the next slide, is another project where we worked on optimization of lead molecules, and I think this was feature set optimization, right? So they're getting the best set to do machine learning by using an optimization algorithm. But these are actually two research projects that we have done internally. So if people want to know more about this, Sam, how can they best reach out? How can they best find out more?
So a couple of ways. Firstly, please get in touch with us if you're interested. If you have interest in these areas, I'd be delighted to talk in more detail and share what we've done and how it may be of interest in perhaps related problems that either you see in other industries or or even in some of the same industries. We are also developing quite a bit of thought leadership in this area at the moment. So expect to see more information of this reaching the public domain in the weeks ahead, because we're keen to share with the outside world some of the exciting work that we've been conducting in these spaces.
Great. So let's not get into the details of this project. It's a fascinating project, but we are also already talking for a while. So let's hear back from you guys. There's another question that we prepared. Just to get a bit of your view, how long do you think it will take before we can use quantum technologies? So we have the first answer, 3 to 5 years, 10 plus years. All right, so that's some people are more optimistic than others. What do you think, Sam? Is it is it 10 plus years, 1 to 2 years? I see one person is very optimistic.
It's a good question, isn't it? And of course, it's the question we all want to know the answer to, and none of us know for sure. I think the question's worded deliberately in quite a general way, and I think in the sort of next few years, so certainly over the next 3 to 5 years, if not before, we'll probably see some very specific applications where there is an advantage. Even nearer still, we'll probably see some quantum inspired use cases where there's genuinely, by thinking about the problems in a quantum way, that there's some benefit and some progress made. But I think that the sort of more widespread adoption and some of the sort of really sort of exciting longer term things that we've talked about will be sort of pushing a little bit further to the future. So that's my guess, is that it's a sort of, you need to sort of take it in two parts, and the first commercial advantage may be sooner than we think, but it'll probably be quite narrow in focus. But how does that compare with your thinking?
Well, I would say that even today we have these quantum random number generators, or even today they are being used to explore physics, right? Like doing physics experiments that have never been before. For example, to study new types of matter like time crystals, or study even very exotic things like wormholes and very, very other cool things. So I think even there, it may not be very commercial, but it is it's a tool that has that is already showing potential or something useful.
I'd agree with that. Yeah.
So given that this is something that is usually important, we don't know when we're gonna see a benefit. It might be a couple of years. For some industries, it may be longer. We saw that there are definitely loads of industries that are impacted from this, right? From financial services to energy to life sciences. And at the same time, it's not easy, right? It's pretty tough to work on this. You need to have at least some knowledge of how these systems work. How do you see that some of the clients that you are working on are approaching this, and how do they get more ready?
Good question. So I think it's a challenge, isn't it? Because it's a field where we know that something is coming, right? We know that over the years ahead, a lot of excitement is gonna occur, and if you're not ready, the risk of doing nothing is actually huge, right? Because organizations who start to get that first commercial advantage are going to be really ahead of the game. So what do we see? I think the companies that are really thinking in a smart way about this are starting to make investments in proportion to that future benefit, and sort of thinking about how their investment will need to sort of scale over time. So first thing to say is that it doesn't take a huge investment to start to build a small team of experts, to start to explore a few use cases, to figure out what all of the challenges are, to figure out how quantum will have a benefit there. But what I think you don't want to do is just do that for a single proof of concept and then stop and say, okay, we understand quantum. When the first commercial advantage falls, yeah, we'll pick it up then, because by that point, the team will have moved on. You'll be scrambling for talent. So I say across organizations, I see slightly different strategies, but I think the really smart movers are the people who are investing and planning a continuous stream of both capability build and research into how quantum's going to have that impact on their industry. What do you see? Does that compare with the sorts of things you're spotting in the industries you're close to today?
Yeah, I think so. Many of our clients are starting to explore this, right? And we also saw this from the Capgemini Research Institute report that we made, where we surveyed 800 companies. Everyone has some people working on this, and I think that there's typically a phase where they start identifying some use cases. That's also something where you, by the way, need a lot of technical, like classical knowledge as well as quantum knowledge, right? You need to combine it to find, where do I have the missing, where do I really miss compute power, and then to combine it with some quantum knowledge to see, would this match, or would this be able to map this to a quantum system, and then to explore, because it's not like a classical systems that you can just run like that. You really have to tweak it. You have to find the right algorithm, see if they actually have speed up, especially for the near term algorithms. It's very heuristically, so you never really know. There's a bunch of things like benchmarks for machine learning, for example, or for other things, but it's not very trivial how they work. So it's really a very in-depth process to explore. And honestly, very often it doesn't work. Maybe the time is not there yet, or maybe the use case is wrong, or maybe something else. But the key point then really is to learn from that, I guess.
Mm-hmm. So a quick question, I guess, is sort of what are some of those learnings that you can take from an exploration into a quantum into a quantum use case, or a family of quantum use cases where they're focused on a particular commercial area? And I think actually we have a slide. Shall I bring up a picture as well? But maybe we can think about these and others.
So I guess that one thing that you can learn is to try to make a resource estimation, like how big a quantum computer do I need for this algorithm, right? So it's not always as easy. Sometimes it's really hard to define that properly. But sometimes you can have some estimates. This is a good use case, but I would need at least maybe 1 million qubits, and maybe, or at least I need like fault tolerant error systems, because I need to have very deep algorithms, and that can be really useful to have a sort of a milestone along the way, right? Like something you identified, something that you learned from, that this will be useful. This is something that I'm gonna watch. And as soon as these quantum computers are better, I'm gonna monitor that. I'm gonna make use of that. And I think that will really help companies into leveraging this better. So,
And I
so
guess
is there one thing that you found most about what you learned from the proof of concepts?
So yeah, really good question, and I have a different answer as well. But one thing I firstly wanted to sort of agree with your answer and actually say, just as a highlight, that I think we've maybe mentioned, but we can emphasize that because of the exponential growth in quantum resource, actually that resource estimation, in some cases it may seem quite a lot bigger than what is available today, but when, as we know from all sorts of things which grow exponentially, and we're familiar with this over the last couple of years, actually sometimes the timescales to really reach quite big scales are not so far away. So that's a sort of important thing, to look at it against vendor timelines and sometimes think, well, hey, if by the end of the decade they really reach 1 million qubits, physical qubits, and actually some of these things we're going to be able to start to tackle. But so I think that is a really good, really good point there. Another thing I wanted to draw on actually from this slide, where we've got a few different things, is actually how it will shape everything else that an organization does, because I think we're sometimes tempted to focus on how can I improve this little bit, as if kind of quantum is in a little box and it's sort of it's inserted into a workflow, and it just makes everything a little bit better for that one area within a business organization. But I think in some cases the disruption will be bigger. You can imagine, just to come back to the example at the beginning, if you really can do more experiments on a computer versus in a lab, then actually maybe it sort of changes the order in which you do things, because you can filter things in or out at a different stage of the process. Maybe you even use your workforce in a different way, so that they focus on, new problems become the limiting challenges in your workflow, and you rearrange to sort of think about those. And so I think in some cases that's sort of those exciting what if questions. What if we could do this? How would it change everything else? And how do we plan for that? Are also quite interesting to start thinking about today, and often open the doors up a little bit more widely than just this sort of very narrow use case, which we sometimes think of in isolation.
So one of the things I think that you the most insightful things that you pioneered, Sam, I think is this perspective, how you can have these different proof of concept that are linked together, and where you can really use insights from different proof of concepts and build that into a roadmap. This slide exactly. What do we see here? How can we how should we interpret this?
So I think this comes from this idea you mentioned, really, that it's not just one POC. One proof of concept often is seen as a bit of a success or a fail, but you've already highlighted that by going down that road, you will learn a lot. And almost certainly, given that this is such a nascent area, you may not end up exactly where you start. So this is just one vision for in the life sciences, a whole set of different streams of research. So we've got a little bit of sort of simulation for drug design. We've got a little bit around quantum machine learning algorithms, including generative models, and we've got a little bit of optimization. And one of the things that I won't talk through all of these in great detail, but each of these in their own right are sort of steps on a journey, and they feed into each other. So, for example, if you learn things about how you can, embed quantum simulations into existing processes, so that you can, for example, treat the study of a molecule exactly embedded in an approximate simulation, you probably learn some things which may help you with machine learning based approaches to be able to use the data that you've got and use that kind of description of the science to put into a sort of machine learning context. And these little links are actually all over the place, I think, between optimization, between the different streams within the sort of quantum algorithms, and but also in terms of the sort of application areas. So it's sort of very much, there are sort of vertical links and there are horizontal links here. And I think that's the way to think about it. Think about where do we want to get to, and what are the sensible building blocks along the way that enable us to learn things that allow us to progress in new directions.
Perfect. So we are almost nearing the end of the hour already. So I want to give everyone the opportunity as well to ask all the questions that you have. Maybe one question that we have touched upon a little bit is that the question from Edwin is, how to get into quantum computing. So I think that one element that we already touched is, there is so much more than just the quantum physics that you need to know. You need to know, what the computational problems are, and not just in a general sense, like portfolio optimization, but what are the specific things that you need to do in there? Is there some optimization? Is there maybe some simulation? Maybe some machine learning? And really, dive that out and maybe put it in the diagram like this. I think this is extremely useful to explore. Do you have any other advice, Sam, on how to how to get started, basically?
I think there are multiple routes to get in, and the nice thing about quantum computing is that there are plenty of good resources. So, for example, IBM have completely opened up a huge amount of materials on getting stuck into quantum algorithms, for example. But another point I wanted to mention is just that there are so many different sides to this where you may be interested to be involved. So yes, there's the algorithm development. Yes, there's a connection with use cases. But we're also going to need an awful lot of related skills, both around the industry problems. There's going to be important and critical software development around actually bringing some of these applications to life and integrating them in future. And so, if you look at the whole area surrounding quantum, there are really sort of many roles and many different skills which are going to be involved in actually driving this forward.
Perfect. So. There was one more question that we prepared, one more Mentimeter question, but so feel free, please answer this one on the Mentimeter. We can have some discussion about it, but at the same time, if you have any questions in the last a couple minutes of the hour, feel very free to address them. So in the meantime, what do you think about this? Hardware, skills, vision, funding, bit of everything, but skills and hardware most of all. Do you agree with that?
I think I'd agree with that, actually. I think hardware has to be there, right? We know that there is a technological journey ahead. We know that everything is theoretically possible, but there are great engineering challenges to sort of get every point to the next level, the next generation of hardware. But we're going to be nowhere without skills, certainly. So it's pleasing to see those are at least two areas which are considered important. What about your perspective? Do you agree with the other areas as well? Or?
Yeah, well, what I think is what you mentioned some time ago is that there is all of our clients that are working on this, they don't have huge teams, right? They don't have thousands of people employed. They have maybe a team of 1 to 10 or something. So everyone is talking in this domain about there's a huge shortage of people. But I think it's not just the people. It's really also the vision, the R&D culture, the culture of learning fast, fail fast. Not having standalone proof of concepts, build them into a roadmap, and feed them into each other. I think that maybe that's maybe a part of vision or something. But that is definitely something that's underappreciated.
And the collaboration between people of different skills having to kind of come together to actually map out that space and provide that vision, clearly going to be.
Funding, I think there's a lot of money involved at the moment. I'm sure some of you have heard about some of the venture capital money that's flowing in, mostly in the US though. So I think it is a challenge maybe in Europe, but also in Europe there are some funding rounds that have attracted hundreds of millions of dollars. So it's quite an active domain. So I wouldn't say that is a very important one, but obviously more money I wouldn't mind. Data, what do you think about that? One vote for data?
I think it depends on the application a little bit. So I think there are certainly some cases where there is data available today. It involves problems that are well understood. I think as we move towards thinking about how quantum will disrupt, there certainly will be some cases where, yeah, we're going to think about what do we need to capture for particular applications. So good that it's on there as well, and certainly something to consider.
I think just like in classical machine learning, one of the limitations of adopting was the right data. Yeah. And I think that would be the true for quantum machine learning as well, and maybe even more important. right? Because you really need to have the right data first. It doesn't make sense to do even the most advanced machine learning, quantum machine learning, if you don't have the basics ready yet.
Yeah. And I hope that this will be part of organizations thinking about the bigger picture around particular use cases. It will be that, well, what else do we need? What do we need to think about in terms of how we acquire data to fit this application and so on? So my hope is that this will grow with everything else as the technology matures.
Exactly. All right, so we are at the top of the hour. So we are really there, so no more time for extra questions. But I would like to invite everyone, if you have extra questions, please feel free to reach out. I see some questions in the chat coming up. I can answer them there now. With that, I would like to thank everyone very much for being here, and specifically also Sam. Great talk. Thank you very much, and I hope to be in touch with all of you. Thank you very much.
Thanks, everybody.
Thank you, everyone.
Thanks, guys.